if you stare into the dead center of a Category 5 tornado, or peer into the eye of a massive industrial whirlpool, you're actually looking at a structural lie.
Yeah.
Which is wild to think about. I mean, we've always been taught that these massive rotating systems, they just sort of die gracefully, right?
Right.
Like the assumption was always that they just run out of energy, they experience this aerodynamic instability, maybe they wobble a bit, and then they just quietly fade away into the surrounding environment.
Yeah, the old paradigm essentially treated a vortex like a spinning top, just losing momentum to friction.
Right.
And for decades, fluid dynamicists and meteorologists, they observed that wobble at the end of a vortex's life. And they attributed the collapse to just a simple decay of kinetic energy just kind of scattering into the atmosphere. Because, I mean, it felt intuitive, right?
It makes sense. Yeah, you think it just winds down.
Exactly.
But so we have this new paper, and it proves that intuition completely wrong.
Oh, completely.
Like these structures do not just slowly wind down. They detonate themselves from the inside out.
Yeah.
Which is just, it's crazy. So we're shifting away from this old idea of aerodynamic instability, and we're moving into this entirely new concept called Thermodynamic-Kinetic coupling.
Right.
So, okay, let's unpack this. Because today's deep dive is focusing on this groundbreaking August 2026 paper by Raj Thakur, and it's called The Unified Theory of Rotational Fluid Breakdown.
Yeah, it's a huge shift.
And it is just this mind-bending look at the hidden, highly localized violence that's happening inside spiraling fluids.
It really is. The shift in perspective here is massive.
Yeah.
Because to understand the mechanics of this self-destruction, we first have to, discard that traditional misconception about the eye of the storm, or, the geometric center of any spinning fluid.
Right, because we always think of the center as the important part.
Exactly. Historically, whether it's in popular culture or even early modeling, we viewed the dead center of a vortex as the anchor of its intensity. But structurally, that turns out to be totally false.
Right, the paper says the exact geometric center of a rotating fluid actually has, essentially zero rotation.
None.
It is fundamentally stagnant, so it acts more like a solid pillar than a swirling void.
Right, and that stagnation is the catalyst for the entire collapse mechanism.
Okay.
The true chaos, the actual process that eventually destroys the entire system, it happens just a fraction of a millimeter outside that dead center.
Wow.
Yeah. Thakur designates this specific area the first off-axis annular ring, or sometimes he calls it the core boundary ring.
First off-axis annular ring. So the fluid in this primary off-axis ring is moving at its absolute maximum velocity.
Right.
But its placement is it's highly precarious. It's basically sandwiched.
Exactly. Sandwiched is a good word for it.
Because on its inner edge, it's scraping against that perfectly stagnant, rigid-like center we just talked about, right?
Right.
And then on its outer edge, it's scraping against the second ring of fluid, which is rotating progressively slower.
Yes, and the resulting phenomenon is what Thakur calls bilateral shear friction.
Bilateral shear friction.
Yeah, because this ring is caught between a stationary boundary on the inside and a slower moving external boundary on the outside. It is subjected to this extreme dual-sided grinding.
I was trying to think of an analogy for this, and it's sort of like, imagine a stationary pole, right?
Okay.
And it's surrounded by a high-speed carousel.
Right.
And then there's a second slower carousel just outside of that first one.
Oh, I see where you're going. Yeah.
So the people standing exactly on that first high-speed carousel, they aren't just moving fast. They are experiencing this violent physical friction from both sides at once.
Exactly.
They're being constantly battered by the stationary pole on their left and the slower moving people on their right.
That is a perfect way to visualize it. And what's fascinating here is the sheer precision of this mechanic.
Yeah.
Because we aren't looking at a generalized warming of the whole fluid body. That bilateral kinetic grinding, it creates an intense internal viscous shear dissipation.
Meaning it's tearing itself apart.
Literally.
Yeah.
The fluid is tearing at itself so violently, and it's restricted entirely to this microscopic annular band, that it generates an extreme, highly localized thermal hotspot.
Wow. Just from the friction.
Just from friction. And Thakur actually provides the mathematical formulation for this. He calculates the combined friction power density, which he called Q dot total.
Q dot total.
Right. And that's derived simultaneously from both those inner and outer boundaries grinding against that one ring.
So the math basically isolates this incredible kinetic punishment to a singular ring.
Yes.
But normally, I mean, if we think about the laws of thermodynamics, right?
Sure.
The heat that comes from that friction, it should just dissipate into the surrounding environment.
You would think so.
Right, it should radiate outward and sort of equalize.
Right, normally it would. But Tucker's paper reveals that the heat generated by this specific annular ring has absolutely nowhere to go.
Which is wild.
It is. The rotational forces of the vortex itself, essentially, they build a cage around that thermal energy.
The cage.
Yeah. The system creates an impenetrable dynamic boundary, and it operates through a mechanism called cyclostrophic balance.
Okay, wait, I have to push back on the physics of that for a second.
Sure.
How does a fluid build a wall out of its own momentum? I mean, we're talking about water or atmospheric air here.
Right.
How does a gas or a liquid act like a sealed bank vault, holding all this heat in without it, just bleeding into the neighboring layers?
Great question. And it comes down to the equilibrium of opposing forces.
Okay.
So in any high-speed spinning fluid, you have centrifugal force.
Right.
And that is constantly trying to throw mass outward, away from the center.
Right, like a merry-go-round throwing you off.
Exactly. But countering that outward push is an extreme inward pressure gradient, pulling everything back toward the center.
Ah, okay.
So when those two forces lock into perfect equilibrium, that is cyclostrophic balance. And when that happens, the boundary becomes dynamically sealed. There is no radial transfer of matter or energy across that barrier at all.
So the fluid is spinning so fast, and the pressure pulling inward is so intense that the heat literally cannot penetrate the wall of its own spin.
Exactly. It's locked in.
Yeah.
And Thakur measures the effectiveness of this entrapment using a metric called the dynamic stretching ratio, or R stretch.
Bar stretch.
Yeah. When this ratio tips above 1.0, it indicates that axial heat removal is entirely restricted.
Okay.
The system has effectively achieved isochoric or, constant volume conditions for that specific ring.
But I mean, you can't just continuously pump thermal energy into a constant volume without a fundamental shift in the state of the system, right? Like something has to give.
Exactly. The laws of thermodynamics demand a transformation.
Right.
With the thermal energy locked inside that specific ring and unable to dissipate, it rapidly converts into massive internal potential energy.
Oh, wow.
Yeah. It manifests as a hyperlocalized extreme pressure spike. And interestingly, the paper actually notes that the energy density in this constant volume ring becomes so intense that it registers a localized mass anomaly.
Wait, really? A mass anomaly?
Yes. A literal, albeit, microscopic, E equals mc squared conversion.
You're kidding.
No, the trapped energy actually increases the mass at that specific coordinate.
That is insane. I mean, that highlights the sheer scale of the energy concentration we're talking about here. Even if the actual mass increase is, tiny compared to the physical force of the pressure.
Right. The mass anomaly is small, but the critical threat is the sheer physical pressure that is accumulating over time.
Right.
And the system can sustain this up to a very specific tipping point.
Okay. What's the point?
It's 95% of the system's rotational confinement limit.
Okay. So let me get this straight. We have a microscopic, ultra-hot, super-pressurized ring trapped inside the very center of a spinning vortex.
Yes.
It's basically a ticking time bomb of potential energy.
That is exactly what it is.
And it's pushing against that invisible wall of cyclostrophic balance.
Right.
So how does the fluid physically accommodate that trapped energy once it finally crosses that 95% threshold?
Well, it doesn't accommodate it. It results in complete catastrophic structural failure.
Oh, wow.
Yeah. Once the internal pressure exceeds the kinetic pressure of the surrounding spinning fluid, that highly localized point undergoes a phase-like shift in how it interacts with the broader system.
Meaning what? Like it changes states?
It effectively becomes rigid.
Rigid. Fluid becomes rigid.
Yes. Thakur refers to this as a speed breaker.
A speed breaker. Okay, here's where it gets really interesting. Because the breakdown isn't just, a simple aerodynamic pop or a slow loss of momentum.
Right.
It's a cascading kinetic collision.
Yeah.
It's as if a high-speed train is barreling down the tracks.
Okay, yeah.
And a massive block of solid concrete instantaneously materializes directly in front of it.
Oh, I like that.
The train cars would just buckle violently inward toward the center while simultaneously derailing and exploding outward.
That is exactly the visual you should have. And if we connect this to the bigger picture, it finally explains why vortices suffer such spectacular deaths.
Right.
Thakur identifies this as the Keystone effect.
The Keystone effect.
Yeah, because the entire macroscopic vortex, the whole thing, relies on that paired in the exact same microsecond with an outward explosion that forcefully tears through all the successive outer confinement rings.
That is terrifying.
It is.
But the paper notes that this violent bidirectional collapse plays out a bit differently depending on the medium, right?
Yes, that's a very important distinction.
Because a compressible fluid, like atmospheric gases, is going to handle that speed breaker differently than an incompressible fluid like water.
Absolutely. The medium absolutely dictates the visual mechanics of the collapse.
Okay.
So in compressible fluids, think of a tornado made of air. The gases will stretch to accommodate that rising internal pressure for as long as possible.
All right, because gas can compress and expand.
Exactly. So the breakdown occurs when the pressure finally overpowers the confinement, resulting in this violent radial expansion originating right from that inner ring.
Wow.
And it physically tears the outer walls apart as the gas rapidly decompresses.
But liquids don't have that elasticity. Like water can't compress to absorb the pressure spike.
Right, you can't compress water. So in incompressible fluids, the trapped pressure solidifies almost instantly into that rigid internal barrier we talked about.
Right.
And the spinning water violently slams into its own unyielding inner wall.
Goodness.
And because the fluid can't compress to absorb the shock, the outer layers are physically shattered the very moment the internal pressure overcomes the kinetic energy of the spin.
So it's just a totally sudden, catastrophic structural shattering rather than an expansive tearing.
Exactly. It's much more abrupt.
I mean, it is a terrifyingly elegant theory.
It really is.
The idea that a whirlpool or a tornado is essentially manufacturing its own internal solid wall, crashing into it and exploding from the inside out.
Yeah.
But, I mean, the challenge here is observation.
Well, definitely.
This invisible collision is happening deep inside structures that are just notoriously hostile to measurement. We're talking about microscopic pressure spikes happening in fractions of a second inside a violent storm or a high-speed industrial turbine. Like, how do you even see that?
You can't see it with traditional instruments, which is why Thakur had to rely on some of the most rigorous 3D computational fluid dynamics modeling ever designed to prove this phenomenon.
Right, the CFD models.
Exactly. And the computational grid parameters he used were insane. They utilized a fully turbulent Reynolds number of 23,604.
A Reynolds number that high?
Yes.
That means the simulation is dealing with a highly chaotic, highly turbulent flow, which is notoriously difficult to process without the math just completely breaking down.
Exactly. And that is exactly why previous models missed this entirely.
Oh, because they couldn't handle the resolution.
Right. To actually capture this localized pressure spike, Thakur's team had to set the spatial resolution, specifically the boundary layer thickness, to an incredibly small 0.15 millimeters.
0.15 millimeters. That is tiny.
It's basically microscopic in the context of CFD. In standard models with coarser grids, the mathematics essentially smear the pressure gradients across a larger area.
Right.
So it's numerically smoothing out the spike so it never even appears in the data.
So the invisible wall was always there, but previous researchers simply didn't have their simulated microscopes zoomed in far enough to actually see the pressure accumulating.
That's exactly it. By pushing the resolution down to 0.15 millimeters, they finally captured the exact moment of failure.
Wow.
So in the simulation, they ignited energy at the exact radial position of 2.70 centimeters.
Okay.
And the model ran normally, maintaining cyclostrophic balance, until exactly 16.71 seconds in.
Okay, so it held stable for almost 17 seconds.
Right. But at that precise microsecond, the model recorded a severe core pressure spike of 221.16 kilopascals.
221 kilopascals. That is roughly 2.18 atmospheres of pressure.
Right.
Concentrated on a microscopic ring inside the fluid, generated entirely by the fluid's own internal viscous shear dissipation.
Yes. And it appeared instantly. It shattered the Keystone ring and triggered the bidirectional collapse exactly as the thermodynamic-kinetic coupling theory predicted.
Okay, but I have to challenge the jump from the laboratory to the real world here.
Sure, yeah.
Because those numbers, 16.71 seconds, 221 kilopascals, they are incredibly precise.
These are.
And they're derived from a 3D CFD setup simulating a highly controlled test chamber that is only 20 centimeters wide.
Right.
The mathematical purity of a small test chamber is vastly different from a massive atmospheric weather event.
Oh, absolutely.
A tornado is dealing with terrain changes, temperature shifts, open skies. Like, how can we map a 20-centimeter laboratory simulation onto a mile-wide vortex in the real world?
Well, this raises an important question, and Thakur addresses the environmental transition by defining what he calls the domains of highest probability.
Domains of highest probability.
Yeah. The theory fully acknowledges that a perfect closed system behaves differently from an open, chaotic environment.
Okay, so the phenomenon doesn't happen universally every time a fluid spins.
No. No. The absolute ideal domain for this thermodynamic-kinetic collapse is a perfectly closed system.
Like what?
Think of strictly confined industrial environments, like sealed rotary pumps or massive industrial centrifuges with rigid end caps.
Okay.
In those machines, axial heat evacuation is physically blocked by the hardware itself. External fluid cannot mix in.
Right.
So the internal ring pressure accumulates optimally, mirroring the CFD math perfectly. And the machine will undergo a catastrophic internal detonation if engineers don't design specific mitigation valves.
So the pump acts as a literal closed thermodynamic box, so the math holds up perfectly.
Exactly.
But a meteorological event is out in an open field. It's not in a metal box.
Right. And in standard open environments, this mechanism is heavily suppressed.
Okay.
Because typically you have free mixing, which is known as entrainment.
Entrainment.
Yeah. Cooler ambient air from the surrounding environment is constantly bleeding into the outer layers of the vortex.
Oh, I see.
And that entrainment continuously bleeds off the localized thermal energy. It prevents the dynamic stretching ratio from ever reaching 1.0, and it keeps the pressure from hitting that 95% critical threshold.
So the storm essentially vents its own heat, neutralizing the internal bomb before it can even go off.
Exactly. But for this Keystone collapse to occur in meteorology, nature has to temporarily trick itself into acting like a closed system.
Wait, how does nature do that? It has to build an invisible lid over the vortex.
Yes, it actually does. It achieves this through intense atmospheric capping.
Capping.
Right. Topographical temperature inversions or rigid stratospheric limits can create a temporary impermeable lid over a severe storm system.
Wow.
And when that atmospheric lid locks into place, the vortex shifts from an open system to a closed one.
So it becomes like the pump.
Exactly like the pump. The latent heat release inside the storm acts identically to the internal friction in our industrial pump. The thermal energy becomes trapped, the dynamic stretching ratio exceeds 1.0, the internal pressure spikes at the core boundary ring, and boom, you trigger the bidirectional collapse.
Which perfectly explains a phenomenon meteorological observers have documented for decades but couldn't fully explain until now.
Exactly.
It solves the mystery of why, right at the end of a destructive tornado's life cycle, the core suddenly fills with intense crushing downdrafts, representing the inward implosion.
Right.
At the exact moment, the outer funnel expands and shreds itself apart, representing the outward explosion.
You got it.
The tornado isn't just running out of steam. It is literally hitting its own internal speed breaker.
Yes. It validates that vortex core breakdown is a product of intense internal pressure generation acting as a singular keystone failure. The very same thermodynamic physics destroying a 20-centimeter industrial pump in a laboratory are responsible for detonating a mile-wide tornado in the real world.
Wow. So what does this all mean? I mean, we are walking away from this deep dive with a completely revolutionized blueprint of the natural world.
We really are.
The collapse of a rotational fluid is not a graceful decay, and it is not a simple aerodynamic wobble.
No.
It is a violent thermodynamic destruction, triggered by internal bilateral shear friction, trapped heat, and a singular keystone failure at the first off-axis ring.
It's the perfect summary.
And understanding this thermodynamic-kinetic coupling, I mean, it changes how we engineer high-speed industrial machinery to prevent catastrophic blowouts.
Absolutely.
And it fundamentally changes how we model the life cycle and the sudden death of extreme weather events.
The theory offers a beautifully elegant mechanical explanation for an incredibly chaotic event.
It really does.
But looking at the strict parameters of Thakur's model, it also leaves us with a highly profound and perhaps, unnerving extrapolation about how we might interact with these systems in the future.
Oh, where does the logic take us?
Well, if we accept the foundational premise of this paper, that the entire catastrophic collapse of a massive vortex is utterly reliant on a highly localized thermal and pressure spike at one exact keystone radial coordinate.
Right.
It opens the door to active interference.
Wait, like what happens if we weaponize that knowledge?
Exactly.
You mean intentionally manipulating the core boundary ring?
Think about the mechanics for a second. A destructive atmospheric vortex, like a catastrophic tornado operating under a temporary atmospheric cap, is relying on a very delicate cyclostrophic balance to maintain its structural integrity.
Right, it's a house of cards.
Yes. It is holding that internal pressure back, inching toward that 95% threshold on its own.
Okay.
Could engineers of the future intentionally introduce an artificial, highly localized thermal spike directly at that precise off-axis ring?
Oh my gosh. By artificially spiking the temperature in that exact coordinate, you push the internal pressure over the kinetic threshold instantaneously.
Yes. By delivering a targeted thermal payload directly to that invisible wall, we wouldn't need to try and blow a tornado apart with massive brute force.
Right, you just need a scalpel.
Exactly. We could artificially trigger the bidirectional collapse. We would be detonating the tornado from the inside out, using its own kinetic energy and structural physics to shatter its keystone.
That is just incredible. We started this deep dive talking about the expectation of graceful decay, assuming things just, wind down naturally.
Yeah.
And we've ended up with the theoretical blueprint for a thermodynamic detonator that could literally shatter a tornado.
It's a whole new world of physics.
That completely shifts how we view the invisible physics governing the storms around us. Definitely something to think about the next time you see the winds start to spiral.